Hello everyone. Now my name is Pawan Kumar. My roll number is 20bq1a04i5, and now I am going to discuss about semiconductors. In this, the contents are origin of energy bands in crystalline solids, classification of solids based on energy bands, chemical bonds in semiconductors, intrinsic and extrinsic semiconductors, Fermi energy levels, intrinsic carrier concentration, p-type and n-type carrier concentration, equation of conductivity, drift diffusion and Einstein's equations, Hall effect and its applications. And now I am going to discuss about the origin of energy bands in crystalline solids. In an isolated atom, there are discrete energy levels such as 1s, 2s, 3s, which are occupied by electrons. If all the atoms of a solid are assumed to be isolated from one another, then they have completely identical electronic schemes of the energy levels as shown in the diagram. When these isolated atoms are brought together to form solid, various interactions occur between neighboring atoms. During these interactions, the higher level energies are affected, considering and consequently the energy levels of outer shell are slightly altered by the principle, violating Pauli's exclusion. And then hence the single energy levels of atoms split into large number of energy levels as shown in the above diagram. Since there are many atoms in solid, so the separation between split energy levels is very small. Hence the split energy levels are almost continuous and are set from an energy band. And if we see empty conduction band, forbidden band, valence band, as these are the three in these 3s orbital, and in 2p is filled, 2s is filled, 1s is filled, and in this 3s orbital here conduction band is empty and the forbidden band, and this is called the valence band. There are energy bands in a solid corresponding to the energy levels in an atom as shown in the diagram. An electron in a solid can have only those discrete energies that lie within the energy bands. These energy bands are known as allowed energy bands, which are generally separated by some energy gap known as forbidden energy bands, or not allowed energy bands. Energy band occupied by the valence electrons is known as valence band, and the energy band which is empty or occupied by conducting electrons is known as conduction band. So this is the difference between energy band, valence band, and conduction band. Now the classification of crystalline solids. How the classification is made. On the basis of forbidden energy gap, solids are broadly classified into three categories, which are insulators, semiconductors, conductors. We see the difference in this diagram only. The conduction band and valency band, if it has the larger band gap, then it acts as insulator. If the conduction band and valence band has a low band gap, then it acts as semiconductor. If the conduction band and valence band has negligible gap, then it acts as conductor. If the conduction band and valence band has a low gap, it acts as semiconductors, and the conduction band and valence band which has a negligible gap acts as conductors. Now let's discuss about the insulators. Solids behave as insulator if it satisfies the following two conditions. Solid has even number of valence electrons per atom. The valence band and the conduction band separately by a largely energy gap compared with kT. Due to large band gap, electrons can jump from valence band to conduction band. In insulators, the valence electrons are bound tightly to their parent atoms. In case of glass, the valence band is completely filled at 0 Kelvin, and energy band gap between the valence band and conduction band is of the order 10 electron volts. An external electric field cannot provide this amount of energy to an electron in solid. And now we discuss about the semiconductors. The energy band gap between the filled and valence band and the empty conduction band is small as compared to the insulators, and more as compared to the conductors. Usually, this energy band gap is of the order of 1 electron volts. Germanium and silicon are common examples of semiconductors. In germanium, the forbidden energy gap is minus 0.7 electron volts, whereas in case of silicon it is 1.1 electron volts. Due to small energy band gap between the valence band and the conduction band, the electrons of valence band can be thermally excited to the conduction band, where they are able to conduct small current on the application of electric field. At 0 Kelvin, a semiconductor behaves as insulator, but at room temperature, a semiconductor has following the peculiar property. This partially filled conduction band, partially filled valence band, or very narrow energy band gap. And now let's discuss about the conductors. In conductors, there is no forbidden between uh, valence band and conduction band. It is observed that the valence band overlaps with the conduction band in metals as shown in the figure. There are sufficient number of free electrons available for electrical conduction. Since conduction band and valence band overlap in the case of metals, so the electrons from valence band freely enter to conduction band. Due to the absence of forbidden gap between the conduction band and valence band, there is no chance of presence of holes. Hence, the total current in conductors is simply due to the flow of electrons only. In conductors, the valence band itself behaves as the conduction band due to the reason metals in general have higher electrical conductivity. So, by this, we can conclude that due to the band gap between the valence band and conduction band, the metals are acts as insulators. If the conduction band and valence band has a lower band gap, then they are acts as semiconductors. If they have negligible band gap, then they act as conductors. So thanks you all for listening my seminar. Thank you.